Let us try to answer the question for what values of p this series converges. Let's write down the general term of the series. This series seems difficult to deal with, so we will try to approximate it using a different related series where the term bn is equal to n over square root of n to the power of p, which can also be written as n to the power of 1 minus p over 2. The thing that we can see in the first glance is that an is less than or equal to bn. Using that notion, we can conclude that whenever the series of bn converges, also the series of an converges. But this relation doesn't tell us whether, if we know that the series of an converges, whether the series of bn converges. We will take a closer look into the relationship between an and bn and their respective series. Let's take a look at the limit as n goes to infinity of the nth term of the first series and the second series. N and n cancel out, and what remains is n to the power of p over n to the power of p plus 4 under the square root. We can take out the square root and place the limit within it, as we can do with any function. We have n to the power of p over n to the power of p plus 4. And finally, we can divide both the numerator and the denominator by n to the power of p, and here we get 1, and here we get 1 plus 4 over n to the power of p. Everything is under the square root. Now, let's sum up our limit, which obviously depends on values of p. When p is less than 0, this limit is equal to 0. When p is equal to 0, we have n to the power of 0, which is equal to 1. 4 over 1 is 4, and it's 1 over 5, and we take square root of 1 over 5. So 1 over square root of 5 for p is equal to 0. And when p is greater than 0, then we have a domination of this term over this term, since this term goes to 0. And the answer in that case is 1. Because of that, we can conclude that if p is greater than or equal to 0, then the series an and bn behave the same with respect to convergence. So either they converge together or they diverge together. This is a stronger result than the result obtained here, which says whenever the series B converges, then the series A converges. But when P is less than 0, then we only can know this. Only this holds in that case. So now, let's use those two conclusions that we made and try to examine the convergence of AN. We will try to see when the series Bn converges and try to spread the conclusion to the series of AN. Let's write down the general term as we've calculated it over here. N to the power of 1 minus P over 2. And now we can use the integral criterion for convergence. Our series of n to the power of 1 minus p over 2 behaves like the integral of x to the power of 1 minus p over 2 dx, where x goes from 1 to plus infinity. Their behavior is the same with respect to convergence. So now, in order to check the convergence of this series, we will check the convergence of this integral. And then we will use our conclusion about the convergence of this series to conclude about the convergence of our original series. Let's calculate the integral. It's an irregular integral, so we will calculate it as a limit of an integral from 1 to b, as b goes to infinity, of this subintegral function x to the power of 1 minus p over 2. So this is 1 over 1 plus 1 minus p over 2, that is 2 minus p over 2 times x to the power of 2 minus p over 2. And we'll need to plug our limit values, lower limit 1 and upper limit b. We take this multiplication constant out of the limit since it doesn't depend on b. We can also simplify it as 2 over 4 times p. And here we have the limit as b goes to infinity of x to the power of 4 minus p over 2 minus 1 to the same power, which is equal to 1. So this integral is going to converge when 4 minus p over 2 is less than 0. Of course, that means that 4 minus p is less than 0. That means that p is strictly greater than 4. When p is equal to 4, this tends to infinity, so in this case we have no convergence. And now we see that this integral converges whenever p is greater than 4. We also see that this series that we used also converges whenever this integral converges. And finally, we can also conclude that our original series converges whenever p is greater than 4. We know that it diverges already for p is equal to 4, and therefore it diverges for all possible values of p which are less than that. So we already have an answer in the part where p is greater than 0, and we can use this answer to reason in general about our first series. So our series converges whenever p is greater than 4, and it diverges whenever p is less than or equal to 4.